Okej. Dobra. Poprzednio, o ile pamiętam, zaczęliśmy trochę mówić o ściśniętej próżni. Tak? Dzisiaj właśnie tak krótko, mam nadzieję, opowiem o tym, że jak między innymi my tutaj w Gdańsku staraliśmy się opisać tą ściśniętą próżnię. Wspomnę tylko, że myśmy tam dotychczas omawiali szczególnie mocno dwa typy, czyli kosz, jeden przez kosz, suma od n od 0 do nieskończoności, tan h, jakiegoś gamma, czy tam h, tan h do n tej k, tu był stan n fotonów po obu stronach i to było dwumodowa ściśnięta próżnia SV, BSV2 i drugi typ, który bardzo szeroko omawialiśmy, to było BSV4, to było 1 przez kosz kwadrat gamma. Dobra, tu było suma tan h do tej k zamiast k, pierwiastek z n plus 1 psi n, gdzie psi n to może być tam na przykład 1 przez pierwiastek z n plus 1 suma j od 0 do n j, tu może być minus 1 j n minus j n minus j j. Dobra. I co? I tą drugą to jest czteromodowa ściśnięta próżnia i ją można otrzymać od biedy po prostu biorąc dwie kopie tej dwumodowej. No i teraz oczywistym jest fakt, że ten stan jest splątany. To znaczy są dwa rodzaje splątania tutaj. Pierwszy rodzaj to jest w ilościach cząstek, tak? Bo jeżeli policzymy sobie na przykład stan zredukowany tego, no to tej dwumodowej, no to mamy 1 przez cosinus kwadrat k tan h kwadrat gamma jest równe n w. Tu jest 2n i k gamma. Muszę się przyzwyczaić. No to jest ewidentnie stan zmieszany, ale wiadomo, że taki stan stwarza pewien problem. To znaczy operujemy z fotonami, a te fotony mają cząstek. Pytania przygotuję jeszcze tam do najbliższych dniach. Dobra, fotony są optyczne, więc mają bardzo wysokie częstotliwości, nie potrafimy mierzyć jak gdyby superpozycji, więc z tego splątania nie za bardzo bezpośrednio możemy skorzystać, chyba że znowu dorzucimy jakiś tam inny stan referencyjny, żeby liczba cząstek się zgadzała po obu stronach. Natomiast jest ten drugi rodzaj splątania, który tu jest wypisany, jest opisany przez fakt, że w pewnych kombinacjach modów mamy stałą sumę czy stałą różnicę cząstek dla każdej składowej. No a jeżeli chcemy się pozbyć już tych składowych, a chcemy, no to wystarczy badać różnicę, tak? W tym modzie jest zawsze tyle samo cząstek co w tym, a w tym co w tym, więc to możemy wykorzystać. Dobra, tu widzę, że pierwszy kryterium, jakim udało mi się znaleźć, ale nie mogłem dziś dotrzeć do tej pracy, to było coś takiego, że jeżeli mam widzialności interferencyjne w trzech kierunkach V1 plus V2 plus V3, to jest mniejsze od 1, to mój stan jest separowalny. Tak się stało, że te widzialności tak się złożyło, że tam VI to było modulus S i razy SI, gdzie S to jest ten operator Stokesa. OK. I wartość własna. Ale mówię, nie mogłem znaleźć oryginalnej pracy, więc tam nie będę się nad tym rozwijał. Natomiast no takim dosyć wczesnym kryterium splątania, jakimś tam miarą splątania dla tych stanów była miara Schmidta. Ilość modów Schmidta. I to się bierze z takiej dyskretnej fizyki kwantowej, tak to nazwijmy, czyli skończenie wymiarowe, lepiej. Gdzie na przykład mogę mieć stan psi, no single out, czyli psi plus, czyli 1, 0 plus 0, 1 na pierwiastek z 2, tak? Teraz jeżeli zrobię ślad częściowy, to oczywiście dostanę ρA równa się 1 przez 2, tak? To ma wartości własne, oczywiście jedna druga. I teraz ilość modów Schmidta szacowana w takiej wysokowymiarowej fizyce, znaczy optyce, to jest K równe 1 przez trace ρA kwadrat. Trace ρA kwadrat. OK. No i widać, że OK, dla nas to będzie w tym przypadku to będzie 1 przez 1/4 plus 1/4, czyli 1 przez 2/4, czyli 2. I rzeczywiście, jeżeli wrócimy do tego stanu tutaj, no to widzimy, że potrzebowaliśmy dwóch stanów separowalnych, żeby stworzyć ten stan splątany, więc to się na razie zgadza, tak? Natomiast jeżeli już się pojawią jakieś nie wiem, jakieś tego typu stany, tak? Czyli 12 13 plus dobra 0 plus tam 1/13, teraz potrzebuję 25 takich stanów, tak, czyli i od 1 do 1/13 do 25 to się równa, znaczy jakieś tam czyli jest to stan bardzo wysokowymiarowy, ale niestety bardzo słabo splątany, tak? Cała dominacja jest tutaj, dobra. Czyli mam teraz aha, dobra, ok. Teraz jakbym to podniósł do kwadratu, to by się okazało, że ok, tu mam wartości własne 144, 169, a tu mam 1 na 169, czyli moje miary, znaczy mój numer modów Schmidta to by wynosił 169 do kwadratu przez 144 do kwadratu plus 25, tak? Ok, widać, że to jest tam no dosyć mała liczba, tak? Jest po 169 do kwadratu, to ile to może być tak z grubsza? No jakieś 300, to też będzie jakieś 144, to jest, to będzie 200, więc to jest tam w przybliżeniu jakieś 1,5, tak? I okej, no jest to, daje to informację, że potrzebowałem jakby jednego głównego stanu, a reszta to tam były drobiazgi, natomiast nie daje to informacji, czy tam 1,4 nawet, coś w tym stylu. Nie daje mi to informacji, ile rzeczywiście modułów wykorzystałem, wbrew nazwie. No ale ludzie korzystali tam z tego miernika. No dobra. I pierwsza, znaczy najpierw opowiem o takiej pierwszej pracy, którą myśmy, dokładniej Marek Żukowski miał, jak zbadać ilość łamania nierówności Bella przez takie stany. Potem opowiem, jaka była historia takich już porządnych nierówności Bella i innych rzeczy. Więc Żukowski, i tam ja też byłem w tej pracy chyba, użył nierówności łańcuchowych. To znaczy mówiłem o tym, że jest tam związek pomiędzy ilością cząstek w stanie A0, A plus dla zera i B minus dla zera. Tych cząstek zgodnie z tą formułą powinno być tyle samo, więc mogę napisać, że n plus od A0 i n minus n minus B0, proszę. Oh, hi. Switch to English. Okay, so I was saying about Bell inequalities for bright squeeze vacuum and like different environment criteria. So, okay, here you have bright squeeze vacuum for 2 modes, right? So I'm using the fact now that in this mode and this mode I have the same number of parties. So this would be equal to 0, right? So if I now take n plus 0 minus and minus some small angle alpha. This is small for small alpha. Small alpha. Okay. Okay. So the idea now is to take many measurements and use the chain bell inequality. So if there was a second column, but never mind. So I'm fixing some measurement at A side. Then I'm fixing a measurement next to it on the B side. Then I'm fixing another measurement on A, and so on, until I get somewhere here. And here I have two orthogonal measurement settings, right? So this would be kind of orthogonal to this, so NA minus NB should be huge. However, in a classical picture, it should be limited. I mean, there should be bound on it. Why? Because I have let's say one minus and b one, okay, plus a two and a one and a two minus and b one and b one, and so on, so on. So you can see this difference of moduli as a kind of distance, right? Because it's zero only for if we have the same angle. So this is kind of a distance. So you can say that you are taking some path, okay, like that. And this path has many intermediate points, has many stopovers on it, so it should be larger. So this must be larger than the direct path, so it should be larger than n BL minus A1, where L is the number of settings on each side, right? So this is my Bell inequality. However, in a quantum case, I just argued that because the correlation between the neighboring settings, which are close to one another, is very good, these all arguments will be very small. And the last one, okay, there's even anti-correlation here. So the last one will be very large. So the whole Bell expression, if you move this to this side, will be quite negative. And that was the first attempt, our attempt to build a Bell inequality for bright squeeze vacuum. So I hope the idea is kind of clear. Okay. Yeah, we can write it, and like we even did some analysis what happens with inefficient detectors. I won't give you any formula for that, but there was a very nice plot which went like that. The violation starts, as we know, for 82.8, 2.8, okay, and it went like that. But here, the more violation you wanted, it took such a shape, and on this axis we have K. So the point is that if you have intermediate efficiency, let's say 0.9, if you want to violate this inequality, you need to increase the gain K, right? But this K, this increase cannot be too big because you end up with some messy state. It has to be just the right, not too small, not too big to have the greatest violation, which is kind of cool. Okay. About the Schmidt number, I forgot to tell you that, like, if you do a plot of intensity, so this will be intensity of A side, so number of photons, and this will be intensity of B sides. These states will show up like that. That here in the center you have maximum correlation, and like elsewhere practically nothing. So the Schmidt number roughly tells you how much of product states you need to reconstruct these bright spots. So of course this is very vague interpretation, so like not very strict, but that's the interpretation that people give to the Schmidt number. Okay, enough about the Schmidt number. So now let's talk how we really got into Bell inequalities for bright squeeze vacuum, and like how did it proceed? Because the hope was that bright squeeze vacuum could be used for quantum cryptography, which was not a bad idea. So for quantum cryptography, you need to have some kind of entanglement or Bell inequalities, as we know from Eckert 91. So one thing that started this whole discussion was by paper by Margaret Reed and I think David Falls, his name is. So that was PRL 53927, 53957, sorry. And the point is that the CHSH inequality works if you have the outcomes equal to plus or minus 1. Okay, you could take some outcomes less than 1 and greater than minus 1, but that would just spoil your violation. So these people were looking for a way to make any reasonable correlation function well behaving, meaning that it won't exceed plus 1 or minus 1. So they proposed that E of alpha beta was equal to n plus alpha minus n minus alpha and that's on A side and B plus beta minus n minus B beta, okay, and divided by, so of course this is not well behaving, but we can divide it by the average number of photons and minus and sorry plus and of alpha plus n minus a of alpha n plus beta b minus n minus beta. Okay, so that's what they did in this paper, and yeah, actually it allows you to construct the CHSH inequality. It allows you to violate this inequality, but this costs an extra assumption, right? And this extra assumption is that regardless of that your correlation function basically depends, the photon number might depend on the number of settings, right? Because you average here over these values. So it might be the case that for whatever reason, if you have diagonal anti-diagonal polarization, you observe more photons than for plus minus basis, right? So that was the point, and also like here it's kind of cheating because the eigenvalues are not between -1 and 1, but just the value of the correlation function. It's so like it's you have this strong nonlinearity of the correlation function. So what we did with Marek Żukowski and Wiesław Laskowski was to introduce ratio. So we took we have rewritten the Stokes parameters, or yeah, maybe not. Maybe now let's how would I describe it? Stokes parameters. Okay, whatever. We have introduced such rates that the rate is R plus, let's say on A side of alpha is equal to n n a plus of alpha divided by n plus a of alpha plus n minus a of alpha. Okay, so that's what we did by introducing this ratio. Later there were rewritten with Stokes parameters, but we will come to that in a second. So the point is that now it's an operator, and indeed it has eigenvalues between 1 and -1, and but the problem, and you don't have to respect that I wrote alpha here and alpha here. It's fine to, I mean, it's fine to use any other basis, but this notation has a neat assumption. So here you would either need to measure the sum of all particles reaching the detectors and averaging separately. That's fine. Or you need to assume that, like for all the settings, the mean number has been the same. Here you just do it on the spot. So of course we assume that you have photon counting measurement detectors, and you know how many photons reached one detector and how many of them the other. And I mean, you could be bothered that I put the division mark here, but you could not divide by an operator, right? This makes no sense. But these operators, they commute with one another, so this is just a handy notation to write that I multiply the eigenvalues of this operator by the inverse of the eigenvalues of this operator. So this is kind of okay to write it like that. And but there is one more problem to be solved, and this problem is even some notes on it. The problem is that you might happen to get a vacuum state, in which case you get 0 by 0. So then we have introduced renormalized ratio operators, which were just projected onto the space of non-vacuum. So 1 minus omega A R A plus of alpha 1 minus omega A. Okay, yeah, so this is how we solved it. And now I will introduce a shorthand notation. So C is just cosh, and S is just, S is, okay, but we'll figure it out. This is sin H, okay. And what? And yeah, let me just look if I have yeah, okay. I seem to be missing. Okay, but never mind. I can write the visibility, and this visibility was equal to of interference. So this visibility was equal to 3 plus C squared minus 4 log C squared of K, of course, minus logarithm of C of K divided by S squared of K. Everything divided by C plus 3 plus 3 cos squared of K. Okay, so now we can actually use the approximations. So I hope it will work fine. So the point is that for K going to 0, it should be equal to 1, as simple as that. And the point is, oh no, it needs not to be. Let's see. So K equal to 0. Sorry. So this is 3 plus 1 minus logarithm of cos K is equal to 0. But divided by S squared is sine squared. But this is still 0, I believe. Yep. No, it should be 1. I'm sorry. This would go to 1 because this would behave like 1 plus cos squared, and this would behave like k squared. So it's 3 minus 1 plus 1 minus 1 divided by 3, and this is 3 cos. So that's not very good, but never mind. Okay, never mind. But for sure, okay, for sure I can get the k going to infinity. And the k going to infinity, I have visibility just 1/3. And 1/3 is a classical visibility. With 1/3 is like attainable for classical states. So does this show that in the limit of large k, we can obtain classical state? And as I remember the graph of the violation of the inequality, it was so that for unnormalized Stokes operator, it was going very rapidly. Traditional ratio operators was going very. No, this is for another paper. Then no, sorry. The point here is that you can now with these ratio operators construct not only the CHSH inequality, but the polytope inequalities like that one, change inequalities. So you have not 2 settings, but L settings per side. And now I had some graph, some table where you could see that the critical gamma is going down. So, for example, for L equal to, I will give just 2 or 3 examples. So this is gamma critical for the method by Margaret Reed and Daniel Watts, and this is our value of K critical. No, I'm wrong. Sorry. Sorry. So this is for these ratio operators, and this is for ratio operators with non-vacuum, right? And yes. So for example, for 2. You have violation up to 915, and here 1.1123, sorry, 1.123. For 5, you have violation up to 126. And here 158, and for 7 you have, let's say, 143 and 1795. So you can see that introducing this ratio improves the situation, that you have more violation. You have violation for higher values of K, right? So you can pump your crystal more, and when you reject the vacuum state, you have still some violation, whereas for when including the vacuum state, you still have you don't have that violation, which would make sense because I mean for these numbers of k, the presence of vacuum state is still significant. So yeah, so so you don't have you are wasting a lot of probability weight on the vacuum state, let's say. And also the conclusion from this paper was that for any number, for any value of k, no matter how strong you pump your crystal, there is a number L that provides the variation. So you can have you can pump your crystal up to its physical limits, uh, and then still have a violation for sufficiently many settings on each side. Okay, I will finish later. So I make a pause in. No, I can't make a pause. Stop capture.